Face restoration has been one of the fundamental tasks in computational photography. Given a low-quality face image, this task aims to recover its high-quality counterpart. Blind face restoration is a more challenging and practical task, where the degradation process of the low-quality image is unknown. Previous blind face restoration methods have achieved great success. They are usually trained on large-scale synthetic datasets with supervised learning, and the datasets are often generated by simulating low-quality face images with a handcrafted image degradation pipeline. Given a pre-trained restoration model, it can produce high-quality restoration on low-quality inputs that are aligned with the degradation distribution used in training. However, it always exists out-of-distribution degradations that makes a pre-trained model fail. In this work, we propose an unsupervised pipeline to adapt a pre-trained model to unpaired degraded images of the target degradation with a much smaller data size. This addresses the domain gap without paired ground truth images or the knowledge of the degradation process. Our method starts with a pre-trained model that does not perform well on out-of-distribution degradation. It is formulated as a pseudo-target generation process, followed by the fine-tuning of the pre-trained restoration model. Given a pre-trained restoration model that produces low-quality restoration outputs, we first generate pseudo-targets using a pre-trained unconditional diffusion model. Specifically, it has a combination of low-frequency content-constrained denoising in early time steps and unconditional denoising for rest of the steps. The generated clean images can be used as pseudo-targets to fine-tune the pre-trained restoration model, without the need for real ground truth images. For low-frequency constrained denoising, we leverage the similar insight as in a previous work DR2, that is when more Gaussian noise is added to the low-quality restoration Y0. The low-frequency content, denoted as phi, is getting closer to the low-frequency content of the noisy image as if we start with the clean image counterpart x0. The level of noise corresponds to the time step in diffusion model. For large enough time steps, the low-frequency content becomes indistinguishable. Therefore, during the low-frequency constrained denoising, we replace the low-frequency content of the noisy image with the counterpart from the noisy version of the low-quality restoration. This guides the denoising process to effectively preserve the structure of the image. For the last portion of time steps, we use standard unconditional denoising to retain visually appealing facial details. The resulting image is the pseudo-target. After obtaining the pseudo-ground truth from the diffusion model, we fine-tune the pre-trained restoration model with the low-quality inputs and pseudo-target data pairs. We apply the widely used image-level L1 loss, perceptual loss, and adversarial loss to achieve good balance of fidelity and perceptual quality. Please refer to our paper for more details. To evaluate our method, we synthesize datasets that contain low-quality images of out-of-distribution degradations. We test our pipeline on two different base models, SwinIR and CodeFormer. The outputs from both pre-trained models contain severe artifacts, while our fine-tuned models are able to produce realistic restoration. We also compare the performance of pre-trained and fine-tuned models quantitatively, and show that our approach consistently improves the pre-trained models. We also compare our best fine-tuned model, the fine-tuned CodeFormer, to other blind face restoration baselines. Our approach outperforms all baseline methods and is able to output artifact-free restorations. We benchmark our pseudo-targets and best fine-tuned model against other blind face restoration baselines in this table. In top rows, we provide results of the zero-shot diffusion-based methods that use a diffusion model at test time, and compare them to our pseudo-targets, as they all require running diffusion at inference time. Our targets achieve the best performance among diffusion-based approaches. The bottom rows show test-time non-diffusion-based models, and our best model improves consistently on all metrics compared to its pre-trained version. At the same time, it achieves overall the best results while being much more efficient than diffusion-based methods. Our best fine-tuned model also outputs the best restoration compared to baselines on real-world testing dataset. Our method only requires a small set of unpaired low-quality images for fine-tuning. We start to outperform the pre-trained model in perceptual quality by a large margin even with only 100 unpaired images. And all metrics improve as the data size increases. When using a relatively larger fine-tuning dataset, our fine-tuned model also becomes much better than pre-trained model in fidelity metrics, as reflected by the PSNR and SSIM. This means that we do not need a very large collection of images to get effective boost in performance, and more data means larger improvements. If you are interested in learning more about our work, please refer to our paper. We have also released our code and testing dataset. Thank you for listening.